state-of-the-art data retrieval with machine learning and Elasticsearch. Today, we're going to be talking about how relevance engines are crucial for an amazing user experience with large language models like Azure OpenAI. So first, just a quick reminder that although most of our demo talks about existing features, we do touch on some possible future features. So some caveats are that these may not exist in the future or may be slightly different than discussed here. So with that said, hello again. I'm Nick Chow. I'm a product manager in Elastic, and I've been working on search here for about the past 4 years. And before that, working in the data science and machine learning space for the past decade or so. With me is Brittany Rausch, the Senior Product Manager of Search, Lists, and Visualizations at Relativity, a legal technology company that's both an Elastic and Azure customer. Joining us as well in the chat are Kim Brill from Microsoft, Nathan Reffin, Jake Cancer from Relativity, and Evan Castle, Jeff Festel, and Nitya Tripathi from Elastic, who will help moderate and answer questions that you might have in the chat. So feel free to drop those questions in there. We are all big search fans, and I'm hoping you will be too after this talk, because today we're going to be talking about how relevance engines are just great for large language models and how they're in fact critical to give a good generative AI experience involving your data. After that, after the why that's important, we're going to show the how we actually make that happen, some of the main facets of good relevance, and how all of that fits together with ESRE, the new Elasticsearch relevance engine for AI search applications. And then Brittany's going to put it all together and show us an example of Elasticsearch relevance in action with a use case from Relativity. So let's start with the headline here. Information retrieval or search, context engines, relevance engines is absolutely crucial to give the context needed for generative AIs to give good answers, good contextual answers that are relevant to your users. So there's a bunch of amazing things that large language models and generative AI have been able to do that are super transformative, but they are limited by the fact that those models are generally trained on public training data. Really, it's the difference between answering a question based on what Wikipedia knows versus answering a question based on what your organization knows. So if you're here, chances are it's the latter that's super important to you. How can you integrate and prioritize your specific knowledge, your specific context into a generative AI experience? So there's a couple really broad ways to do that. The first is, of course, with fine-tuning. You can train your own large language model or fine-tune an existing one, but that's generally an expensive proposition. And sometimes it's not even feasible. You might not have enough data. It needs to be labeled, often manually. And of course, you need a deep data science expertise. We're really going to focus on the second one here, which is creating context windows for any user queries or any questions that you might have. So ultimately, useful context windows are what you need in order to have a generative AI experience for your specific organization or your specific users that rely on your often non-public data. So what is a context window to start? When you generate a prompt, a context window provides additional information not provided by the user, which helps the large language model kind of provide the right answer. So to put that kind of in an architectural flow here, if a user asks a question, the first thing we do is we go through that relevance engine, that supporting search for a generative AI. And we use that, we find a short list of really specific documents or subsets of those documents, which we provide in the context window. So you have your prompt, which is like you are an HR manager or what have you, and you're answering these questions, and you have your context window, which includes both the chat history and in this case, supporting documents. So of course, then comes kind of the first big question. Well, why use a search engine at all? Why use a context engine? Why not just dump all of your engine into the large language model context window? So the first really easy answer is that you simply can't. There are token limits, both from the realities of the size of the model and the amount of memory that it consumes, and just simply model limits. So for example, if we take your average, let's say 3-page document, so that's about 1,500, 600-ish words. With current ChatGPT-4 model limits, there's two options there: the 8K token limit or the 32K token limit. If you completely fill up your prompt token limit with just 3-page documents, you get under 4 or 15 documents. So it's not a lot, and it's certainly not your entire corpus. And that absolutely doesn't include your prompt, which can get much bigger with a lot of prompt engineering, or chat context, the super important chat history, which kind of helps keep that continuity in your experience. Even if you were able to fit a bit more, it's super important to only fit the documents that you need. And there's a couple of reasons for this. The first is cost optimization. So if you have a really sloppy retrieval system and you kind of leak documents that are less relevant, that really kind of hinders any sort of cost optimizations you have. To put this kind of in context, at a modest scale of only 1 million searches a month, if you fed a whole documents, this is a bit of an extreme example, but if you fed whole documents into your prompts, that alone at the 8K model size will cost you about 225K, whereas with the 15 documents, so the 32K model size, $1.9 million for 1 million queries. And that's, I mean, really, if you're looking at $2 a query, considering search is often measured in terms of tenths of a cent, you're looking at multiple orders of magnitude for slippage, for waste. Of course, that value optimization might matter, can be used for a lot better things. So for one, that opportunity cost for other context. So being able to bring the context that actually matters rather than some documents that might not matter is, might be a trade-off that you have to make if you have a less relevant engine. And the other one is, of course, compute time. Even as over time, model limits become bigger and costs become cheaper, compute time will always still matter. And for applications like e-commerce, where conversions are impacted by milliseconds, that compute time really comes into play. So to summarize that big part, you really need kind of a really tight context window, a really good information retrieval system for large language models. So let's dive into how ESRE can be used to build that good information retrieval. So I'm going to walk us through a really kind of like quick architecture here. You've got your chat application, you've got your user, and you've got your large language model. And in this case, you have your relevance engine for AI. That's ESRE. So your user kind of adds their human chat input, their question. They submit it to your chat application, which, rather than sending it directly to the large language model, issues that as a query in the document store, ESRE, which then takes relevant documents, a subset of those relevant documents, and adds that to a prompt template, which is then sent to the large language model. The AI completes that. And then you get the reply. So the part that I want to focus on today is step 2. How do we generate those relevant documents? How do we get those relevant documents? This is kind of the really exciting part. So let's see how all of these work. We've got kind of 4 major subsets of relevance, and I'm going to set us up with a little example here. So here we've got an example workplace search. We've got an example workplace search kind of use case. So organizational information inside a data store, and we're a new user who's just onboarding. So they're asking a bunch of various questions around how the organization works and maybe other kind of questions like that. So the first big piece here is semantically similar documents. So that's asking what documents are most like this query, that are most related to this query. So let's take a look at that. For example, we can ask to start, does the company own my side hustles? The other terms besides side hustles are kind of very broad, but what I really want to highlight is the fact that side hustles are not likely a term that appear in, for example, an intellectual property policy. And in this case, it certainly does not. What's amazing that kind of helps fuel that are a few things to provide that right answer. The first is vector database search. So actually being able to encode your query and all of the documents and finding the most semantically similar in kind of a mathematical model sense documents. The second piece there is natural language processing enrichment, really embedding additional context into those documents to help kind of enrich it, to provide more kind of tokens or grabbable pieces to search. The third there are sparse interaction, learned or late interaction models, such as ELSA, the Elastic Learned Sparse Encoder. And that is a really promising new technology that's just coming up, or application of it that's just coming up, where you get your kind of like broad semantic understanding alongside your speed, alongside your token matching speed. And of course, the last one is regular token matching. So that's BM25F, the ability to find specific words or phrases or sentences that match. There is so much that we want to go into here, because when you combine it all with a hybrid technique such as RRF or linear combination, benchmarks have shown that you get even better results than in isolation, than with just a vector database search, for example. There is a ton of more detail that we want to go into, but stay tuned for Michael and Brittany's talk around why vector search isn't enough, where they will dive into a ton more details. The next piece here, and this is the part where just content isn't enough, where just having a vector database with content isn't enough, and that's non-content signals. So there are other document characteristics. There are other parts of the document that could signal relevance to either that query or in general that kind of make that query more, that make that document more important or interesting. So for example, if we ask, what is the work from home policy? In this case, this fictitious organization has had multiple updates. They've had about a dozen or so work from home policy updates over the past 2 or 3 years since 2020. And in order to feed the right context without having to throw all those documents at the large language model, we've added a time decay or a boost, an additional signal boost based on the freshness of the document. So here you can see that the documents have come up, included some updates from April, an update from May, as well as the original work from home policy, allowing the large language model to use the freshest information to give the good answer. Besides time proximity, there's a bunch of other non-content signals that could be important depending on your use case. This includes things like geolocation, so proximity to a user's location. So for example, office locations or store locations, engagement, whether that document has had a bunch of comments, plus ones, reactions or things like that. And as well, data that's not user-facing. So things like conversion rates or page views are also super useful content signals that can be boosted on, and that structured data combined with that content search really kind of brings to life. The third one, and I think one of my favorite examples here, are domain-specific contexts. So how can your organization's slang or tacit language fit in a world of general models? Don't forget, models are trained on a kind of really broad data set. So when you ask a question, in this case, like what is NASA? A generally trained model can and does respond with, well, it's the US Space Organization, or National Aeronautics and Space Administration. In our case, it stands for the sales team that's in the North and South American region. What's really cool about this example is that document doesn't include this term. It doesn't include NASA, which would be hard to find. There's no semantic similarity here because NASA is simply an acronym. But what's really neat is by using some core search tooling like synonyms, we're able to connect an organizational word like NASA to a kind of a broad kind of meaning, which, extra cool part, the large language model is able to decipher and encode on our behalf. So nowhere in here do we say NASA is the North America, South America region. The large language model was able to put that together, given the data that we've fed it. So besides tacit language, there's also things like within your organization. There's, of course, maybe in your use case or domain, there's specific terms. For example, an account in the legal world is going to be very different from an account in the finance world. As well, it's also used for things like SKU or product codes, because if you've got just an arbitrary set of strings and numbers, letters and numbers, it's going to be really hard to tie that to any sort of semantic or token search. So being able to map that really kind of helps enrich your documents and relevance. And finally, and this is the one we get a lot, and that's how can we actually get signals from what we know about the user? Personalization, like about who the user is or what they've told us to generate context for that individual. So as an example of that, if we ask so our user here is asking, how do I update my tax elections? So I'm in Canada, and of course this answer is going to be really different from depending on the country you're in. But because we know that context, the user doesn't have to feed that in, because our application knows that the country I'm in. It's able to provide a regional specific answer. This, of course, is a really broad example. But as you can imagine, you can dissect this into kind of even tighter cohorts or sections. I'm going to mention this as a subset of personalization, but I think it's just important on its own, and that's the idea of document level security. So the idea that as someone with a specific role, they may not or should not have access to specific documents. So for example, in this case, you'll notice up in the corner, we've got an engineer role right now. If this engineer asks, how does compensation work? In a real company, in a real organization, of course, I'm sure we'd have an answer that points folks to something like, a job leveling matrix or a policy, but we really wanted to highlight to kind of overemphasize the fact that you could cut out documents. So in this case, we've chosen not to provide, to cut out those documents that don't work, that don't fit this role, which the engineer should not be able to see. But if we switched to a manager role, you'll notice that all of a sudden we have documents that are much more relevant to that question. So in this case, it's a compensation framework, something that needs only be shared with specific roles. There's a whole bunch here around personalization. So to kind of like split that into those two main points, the first is personalizing data for someone based on who they are. So their demographics, their role, their location, or what they've done. So the behavioral patterns, like what they've clicked on, what they've searched for, what they've bought in the past. On top of that, another incredibly important part of this, especially for something that might involve your proprietary data, is document and field level permissions. So that's making sure that specific roles can see specific documents, but not others. And not just on the document level, but on a field level, making sure that some roles have access to specific sets of information within a document and not others. A great example of that, for example, would be if you're an e-commerce use case, and you might have different prices for different regions or different resellers. So we've gone through a lot here. So we're just going to take a quick breath. We've seen an example where Elasticsearch can provide valuable context for a workplace search use case. But this same technology has so many applications for so many different types of use cases and scales. So I'd like to scale up, as it were, from this example where we've got maybe thousands of documents in an onboarding scenario to an example which involves hundreds of millions of documents and a very real impact to people's lives. I'd like to welcome Brittany Roche, who is going to show us how Relativity combines both Elasticsearch and Azure to help bring justice to people around the world.
We are a legal tech platform that provides or that specializes in data discovery for litigation and investigations. And so some of you may not know what e-discovery is, and that's totally fine. In a legal dispute, counsel has an obligation to preserve, collect, identify, and ultimately share relevant non-privileged information with the opposing party. This is called the e-discovery process, and it's critical to fact-finding and case strategy development. In investigations, data discovery is just that. It's identifying evidence to help you build your case. And so if you really break it down, we help legal teams do three things: organize data, discover the truth, and act on it. And so you may not have heard about us, but you see the work our customers do in the platform every single day. And so we wanted to show you what Elasticsearch and the ESRE technology can do for our customers in Relativity. And one of the biggest issues that our customers is facing is just like an absolute mountain of data that they have to get through. The data growth explosion has hit our industry particularly hard. Our users have to go through Slack, email, text messages, WhatsApp, I mean, you name it, we've probably dealt with it, hundreds of applications and file types. And so we want to highlight what a very like real case would look like. So picture this. You're an investigator for the EEOC, and you've received a case of two undocumented immigrants who were recently fired from their positions and subsequently deported. The case revolves around Big Thorium, a fake company, just for reference, who put out a call for workers to build its new power plant in Texas. Our claimants are welders. A local recruiter offered them a spot on the crew, but they had to upfront their processing costs. So they sell their homes, they pay $20,000 in fees, and they head to the US. Now, there's a number of different facts that we'll see with this case. So a month later, the workers found that they were segregated and put into housing that was very low quality, and they had to pay for the pleasure of living there. They were promised green cards, but those green cards turned out to be temporary work visas, and they'd leave, but management is holding on to their passports, and they're just unable to get that documentation back. Not only that, but management is garnishing their wages for additional fees, and anytime they complain, they're threatened with physical violence. Two of the workers decide that they're going to whistleblow to a local news agency, but they didn't realize that their messages were being surveyed upon, and they were fired and deported. And so, like, this seems very, outlandish, but this case is actually modeled off of a case that is right now being litigated by the ACLU. And these are the type of cases that our customers work on every single day. So it's really important that we help them get through their data. And so I'm going to go through a live demo. Again, please bear with me because Chrome can be tricky. Everybody can see my screen? Nick? Okay, great. All right, and so because our users have to go through this just absolute mountain of data, we need to bring in AI to help them get into the specifics of what they're really looking at. And if you think of a data collection, they're going into a user's inbox, they're taking an image of their phone, they're looking at their entire contents of their computer, and they have to dig into that and get through all the junk. And so that means getting through the sales emails, the calendar invites, the conversations about where to go for lunch. And so the way that we are envisioning doing this is by using a combination of large language models like GPT-4 and ESRE to bring in the facts of a case. So everything that I just mentioned that we know happened in this dispute, we would call the complaint, the facts of the case. And so we would use categorization here to be able to identify the documents that contain facts pertinent to or pertinent to the case. And so in this case, I want to look at entities because at the heart of any matter are the people involved, and entities are the nouns, the people, places, things. And so I would use different technologies to be able to extract those entities and then take a look. In Relativity, we have what we call the communications analysis. And so this is a visualization that allows us to see how people are talking to one another. And we also have an AI model called sentiment analysis, a little bit different from the marketing tool. This is tailored specifically to our use cases. And so that allows us to see the sentiment distribution between communications. And so one thing that as an investigator that would pop out to me is that William and Francis have a lot of red around their names, and that means that they're saying things in a very angry way. And so using ESRE, I could ask a question. I can interrogate the data. What is this negative communication that they're having? And pull back specifics around what they're discussing. And that allows me to then dig into those 6 emails. So I've gone from 56,000 documents to 6 documents, and those 6 documents are probably very relevant to the conversation. But it doesn't stop there. I can also take a look at pay cuts, because we know pay cuts happened. And the signal detection here immediately picks up on workplace retaliation. And that's a big one if you're doing this kind of investigation. And so I'd want to take a look. And then I have a number of different documents that come up with related concepts. And so using this kind of conceptual searching, I then go into our viewer and look at it. The viewer highlights the different kinds of conversations that are happening and the things that are most relevant. Also has some logo detection and other nice features. But this is what we would call the smoking gun. And so while that doesn't always happen, happens more than you would think. And so this is the kind of thing that we would immediately hone in on. And so that's our demo. And I thank you all for the opportunity to share the work that we're doing here in Relativity.
Thank you very much, Brittany. That was a wonderful demo. Yeah, that's so super inspiring. We love seeing kind of our technology and our work being used for good like that. So we are coming up to the end of our time here. Just to sum up, we've talked a lot about kind of relevance and all those relevance toolings, and our timing is super great right now because I think you are the first group of people to see this right after we've announced the Elasticsearch Relevance Engine. So we're right on the edge here. That relevance engine that allows you to put together all of those relevance pieces from a vector database search to structured data search, all the way through to, Brittany mentioned, they have multiple machine learning modules. And being able to incorporate those into your context engine to feed your AI experience. So yes, that Elasticsearch Relevance Engine is available today. But as we wrap up, thank you so much for joining us. We have another session that I alluded to earlier with Brittany again and Michael Hildebrandt called Why Vector Search Isn't Enough. You'll learn a whole bunch more around those search techniques. And finally, if you are interested or have any want any follow-ups, please check out our website at ela.sd/buildvectorsearch. That's build vector search with hyphens in between. Thank you all and enjoy the rest of MS Build.